Hello everyone, welcome to this webinar where I will be discussing how we can augment our usage of Abaqus using scripting in Python, and especially in Python 3. See that people are still joining. Okay, let's proceed. So today I will start talking a bit about why we might want to use scripting, what it's good for, and why Abaqus uses Python specifically, what Python is. Then we'll look a bit closer at where the Python commands in Abaqus come into play, the different files that are involved, and then how we can apply the commands and use them in macros and scripts, and then take them to the next level, which is plugins. And lastly, we'll look a little at what's been added recently to the Python interface of Abaqus in recent versions. And in particular, we'll look at the most recent update of Abaqus, where we have switched from Python 2 to Python 3. Some notes on the background to that, and what we need to be aware of in this context, and how we overcome the issues that come with it. So what is scripting good for? The fundamental application of scripting is to automate tasks. And obviously this frees up time and resources that we can spend in a more valuable way. But it also allows us to minimize human error, since it makes sure that whenever we execute some task, it gets performed the exact same way every time we do it. And it also allows us to extend the functionality of Abaqus, unlocking more advanced procedures that we can do. For example, when we pre-process, we can do things such as create one connector for every node in a certain region. We can do advanced post-processing. If we compare to some built-in features like operating on fields, we can do more arbitrary operations, combine arbitrary steps or frames, and do basically any mathematical operation that we want. Another thing that's useful for scripting is that if we can execute variants of the same analysis a large number of times. A typical application for this could be a design of experiments or a parametric study, where we first use scripting to perform changes in the model. Then we can run the models, and then afterward we also use scripting to extract output from the many different analyses that we have run. And scripts in Abaqus use the Python language. It's a scripting language as opposed to what you might call a high-level scripting language, as opposed to what you could call a low-level programming language. And it has some desirable properties for this purpose. It's free and open source, and it's portable, meaning that it runs on all major platforms. And it's mixable, meaning that we can mix it with other languages whenever we need, in case where those might perform a specific task better than Python. And now that we know a bit about Python, we can see where it comes into play in Abaqus. So whenever we perform some command in Abaqus CAE, that always corresponds to a Python command. And these Python commands will actually be stored in a couple of different files. First, there's the recovery and journal files, which end in rec and JNL. These store modeling commands, so commands that affect the model. Example of those would be if we create a part, or if we assign a section to region. So these are always associated with a model database, and these files will be in the same directory as the CAE file. And the difference between the rec and JNL file is that unsaved commands go to the rec file, and whenever we save the model database, they are moved to the journal file. So you could say that the journal file is just, as the name suggests, a journal of all the commands that have been used to build the model. And then the fact that we have a rec file that stores unsaved commands is useful if in the case of a crash, for example, because that lets us recover the commands that were not saved in the model. The third file that saves Python commands is the replay file, which has the file extension rpy. And this does not only save modeling commands, it saves all commands. So things such as creating viewports or modifying the camera, or post-processing commands such as contour plotting or creating XY data, they're also saved to the rpy file as opposed to the other two files. These are not associated with a model database, but with a session, and thus they are located in the work directory instead. So how can we take advantage of this? Well, we can use macros and scripts. That is fundamentally how we automate things. There is fundamentally no significant difference between a macro and a script. Both of these are sequences of commands that we can execute as if it was only one command. In the context of Abaqus, the main difference is that macros are usually something we record of ourselves when we perform some commands in Abaqus CAE. So it's typically a very specific application, whereas a script could be something more general and customized and so on. So everything that has to do with macros in Abaqus is handled through the macro manager. From the macro manager, we can create a macro and run it, and we can also delete existing macros. Scripts, on the other hand, they are mainly run from Abaqus CAE in two ways. We can choose file and run script, or we can run them from the command line interface, which looks like this, or we can use the command exec file followed by the file name of the script to execute the script. Another option, if we don't want to run it in a current session, is to start a new Abaqus CAE session with the script on startup of the session. This is done using the command Abaqus CAE startup or no GUI. The difference between these is that the no GUI version does not leave an Abaqus CAE session running after the command has completed. And now I will show what it might look like when we record a macro. So first we start the macro manager, and then we record a macro by clicking on create, and then we can choose to save it in the home or work directory. Now recording has started, and the idea is that we create a part. So this is useful if we, for example, have a certain geometry that we use a lot in our projects. So we will just create a sketch as normally, and then apply some constraints. It's important to apply the constraints because the idea is that we want to customize the dimensions of the sketch later. So the constraints make sure that everything ends up in the right place. So we have the equal distance constraints to make sure that the circle ends up in the middle, and a fixed constraint on the corner to make sure that that corner always falls in the same place. And now we add some dimensions to the sketch. We choose a side length of 20, and then we'll enter a radius of 5. And then the sketch is done, so we choose an extrusion depth of 10. And now that the part geometry is finished, we can stop recording. If we run the macro right away, then nothing happens because it will just try to create a new part with the same name as the old part. So in order to demonstrate it, we first rename the old part. Now we can run the macro, and we see that a new part has been created that's exactly like the one we just created manually. And a next step to make the macro more general and interesting and useful is that we can add some interactive input to it. This can be done with the Python function getInput. So what it does is that it pauses execution of the script and shows a dialog box, and then it will wait for the user to provide an input, after which the script will continue with the input that the user gave. In this simple example shown on the right, it takes the input provided by the user and stores it in the variable user input, and then it prints what the user just entered in the dialog. Perhaps not the most useful script, but you get the idea. And then there's a variant of the getInput function called getInputs with the S at the end. And this allows us to provide multiple inputs in one dialog box. And I will show how that might look. So if we want to modify the macro, that actually requires a little bit of coding. So we first need to open the macro file, and we need to remember where we chose to save it, in the home directory or the work directory. It's always called Abaqus macros.py. And all of this code might be a bit hard to understand, but we can remember that we chose 20 as the side length. So then we can identify that probably this is the line that assigns the side length to the square in the sketch. So what we want to do is to let the user interactively input the side length, and we can do that by replacing the value with a variable that we call side length. And now we assign a value to the side length by using the getInput function. So the macro will wait for the user to provide a value for the side length. And the last thing we need to do is to convert it into a numeric format. Because when we use the getInput function, it will be a string that's returned. So we need to convert it to a floating point number in order for it to be usable as a side length. After we save the macro, we can then run it again, and we see that the sketch is created, but now we get prompted for a side length. And when we accept, then the macro goes on and actually creates the geometry with the side length that we have specified. And we can take this one step further by looking at plugins. Just like scripts and macros, these extend the Abaqus CAE functionality in some way, but this also adds a little bit of customization to the GUI. Abaqus CAE is already shipped with a few plugins that you may or may not have used, such as the Additive Manufacturing Modeler, the find nearest node plugin, which returns the nearest node given a set of coordinates, as well as the Excel utilities plugin, which allows us to couple Abaqus with Excel. There are two categories of plugins. There are kernel plugins, which alter the state of the session. For example, if we make a change to the model, or we do some post-processing commands, these require a kernel plugin. Whether a GUI plugin could be something that helps the user select a set of nodes in the graphical user interface, given some certain criterion, depending on what the plugin is for. And when we connect a plugin to Abaqus, can either be added to the plugins menu like this, or it can be added to a toolbar or toolbox like this. If you want it to be a little bit advanced and have a customized dialog that's more complex than the one I showed you, we can either code it, or we can use the RST dialog builder, which itself is a plugin that helps us build the dialog box for it. And RST here stands for really simple GUI, so that might be good to know. So plugins are loaded when Abaqus CAE is started. It mainly searches in 3 folders for plugins. 2 of them are called Abaqus_plugins and located in the home directory as well as the working directory. We can also specify an arbitrary directory by editing the environment file and setting the parameter plugin central dir to whichever value we want Abaqus CAE to look at. So Abaqus CAE will look through these directories on startup, and if it finds a file with the suffix _plugin.py, this is assumed to be a plugin. Generally, for every plugin, there are 2 files required. First, there's the actual code that in the end will be executed by the plugin, and that is in Python format. And then there's a registration command, which does not contain the end code to be executed. Instead, it contains a command that adds the GUI connection into Abaqus CAE. So this is what will have the suffix plugin.py, and it's recommended that the prefix of the registration file should be the same as the actual file that contains the code to be executed. And it's perhaps not surprising that the registration file needs to look a certain way in order for it to work properly. So here I'm showing an example of a registration command, which we would use if we want to add the plugin to the plugins menu in Abaqus. We need to call the register kernel menu button function. And I should mention that this code is not something that you have to memorize. An example like this exists in the Abaqus scripting guide in the documentation. So first, we specify some text that should be shown on the button in the plugins menu to refer to the plugin. Secondly, we specify the name of a module that this will call. So this should be the same as the file name of the actual plugin code, except without the file extension .py. And in that file, there should be the code that we execute should be organized under function. So in the last parameter functioning, we specify the name of the function. So when Abaqus CAE starts and loads a plugin, some commands will be sent to the kernel based on what we have entered here in the registration command. First, it will import the file that we have specified as a module, and then from this module it will call on the function that we have specified. So that's why it's important to keep track of the way we name the files as well as the functions within those files. Next, we can move on and see what has been added recently into the Abaqus scripting interface. In Abaqus 2020, we saw a major change with the addition of 3 Python packages. Just to be clear, these existed independently in Python before. This is just when they were added into Abaqus. So first we have matplotlib, which is a wide package for plotting. Then there's SciPy, which is a general toolkit for scientific applications. It contains modules for example, interpolation, optimization, signal processing, Fourier transforms, and so on. And thirdly, in Abaqus 2020, the library SymPy was added, which lets us do symbolic computations in Python. And in the most recent version of Abaqus, Python 2 was abandoned in favor of Python 3, and this has some important implications, which I will start going over now. But first, a little background why this change was necessary. So Python 2 was released in the year 2000, and Python 3 was released 8 years later. It contains some general improvements regarding performance, security, ease of use, and many other things. And it was intentionally designed to not be backward compatible. So since then, more and more codes have migrated from Python 2 to Python 3, and this last year it was time for Abaqus CAE as well. So now Abaqus inherits all of these numerous improvements and updates, and we can also benefit from newer versions of all the libraries when we use Python 3 in Abaqus, since a lot of the libraries abandoned Python 2 a while ago. As I said, Python 3 is not backwards compatible with the Python 2. So I will go through a little bit of the things that have changed, at least the most important things. So printing and integer division is something that probably will affect most users. But there's also things such as module imports working differently. And Python 3, unlike Python 2, has a clear distinction between byte strings and Unicode strings. And it relies more on iterators, where Python 2 would use lists, but those I will not go through in detail. So where does this change impact Abaqus? Theoretically, any functionality in Abaqus that uses Python syntax will be impacted. However, there's a scale from very small to very large impacts, and I can show on the bottom of the ladder. It's things that could theoretically be impacted. We have expression fields in Abaqus CAE, and we can perform parametric studies using the parameter keyword or PSF files. And all of these accept Python syntax. However, I don't think it will practically change anything. So we can move on to the next level, which is environment files. So some users might have customized startup applications in their environment files, and these might not work correctly in some cases, especially not if they contain print statements. And then on top of the ladder, we have things such as scripts, plugins, and custom applications, which in general will not work at all in a Python 3 without without checking them first and making sure that they do. So I will talk a bit specifically about which things change and what we can do about it. First, there is printing. In Python 2, printing was a statement, whereas in Python 3, printing is a function. The most obvious change is that in Python 3, we need to have parentheses around what we want to print. Some more subtle changes is that since print now is a function, it has the same properties as any other function. So we can pass the print function as an argument to other functions, and we can even override the print function and make our own custom print function if we wish. And another change is that there's now some optional keyword arguments, sep and end, if we want to customize how the output of the print function looks. And what do we need to think about when we're upgrading? Well, one thing that is that Python 3 syntax actually does work in Python 2 as a coincidence if we are not using the sep and n arguments. And if we want to handle the upgrade a bit more rigorously, we can import the print function into Python 2 using from future import. The next thing that is impacted is the behavior of division between integers. In Python 2, division between two integers always results in an integer, and this perhaps seems unintuitive and unexpected, but it is actually consistent with how many older programming languages handle integers, because there was a very strict distinction between integers and floating point numbers. However, this distinction is arguably not very useful for practical applications, especially for those of us who are not computer scientists. And Python 3 does not return an integer in general when we perform integer division. Instead, it performs so-called true division. If we still want to force integer division, we simply use a double slash instead of a single slash, and this works both in Python 2 and Python 3. And to help us upgrade, we can import the division behavior into Python 2 using the future module, just as before. I mentioned the future module regarding printing and division, so just some quick notes about that. There are also some other features that we can import from the future module, such as the handling of Unicode versus byte strings. And there are also some more advanced features that I will not mention here, but it's good to know. And the future import statement is a bit special compared to other import statements because future imports must be at the top of the file. It cannot be after any other commands except for other import commands. Luckily, to help us, there is a built-in tool in Abaqus that helps us convert script. I've gone through some of the syntax changes that affect scripting in Python. So this upgrade script will automatically apply all these syntax changes and some more that I did not go through today. And if we are feeling uncertain about this conversion script, we can actually preview the changes before saving them. You have the option to convert individual files or a whole directory if we wish. And if we do not wish to use the GUI, we can upgrade using the command line with the command abaqus python abqpy2 to 3. And I would like to mention that in my experience, this works quite flawlessly. So it's actually quite easy to convert your scripts to work with the Python 3. And now, clearly, you're not going to be scripting experts just after listening to one webinar. So I would like to point out that we are going to have some scripting trainings in the near future, both for beginner and advanced levels. We will have some in German in March and in English in April. Some other helpful resources for learning is the Scripting User's Guide and the Abaqus documentation. And you can also attend an online training course and study at your own pace. We at TECHNIA are also happy to offer one-on-one trainings as well as consulting services to help with your scripting applications. And that's it for this webinar. The next webinar will be about cohesive elements and contact, and it will be on the 28th of March. And thank you very much for attending. If you have any questions at all, please contact me at oskar.smedman@technia.com. Or if you have any inquiries regarding training or consulting, reach out to sales.simulation@technia.com. I wish you all a happy weekend.